everybody, and welcome back to another video of Turbos, where we're just going to be expanding and factorizing things. And then in the end we'll do some HMMT questions. I'm pretty sure that's Harvard stuff. So the first thing that we're going to be looking at is x plus y squared. And how we can proceed to solve this is literally to just bash it out, which basically means to expand it. So you've got x squared plus xy, and then we have, I'll do it in green, why not? We can move the y to the x and the y, so we have xy and y squared. And if we add that up, we'll get our final answer. X squared plus 2xy plus y squared. And that's basically how we're going to proceed to, prove all of these expansions. So what we can do for the next one is simply expand again. We can move the x to the x or to the y. So we have x squared plus xy. And then we can move the y to the x or to the y. So we have minus xy minus y squared. And these cancel, so in the end we get our final answer of x squared minus y squared. Next, that's how we're going to proceed to solve all of these. I'm just going to fast forward this. So we basically, in that time lapse, we just said that this, I should use, okay, this equation equals to this, and this equation, x minus y times x squared plus xy plus y squared equals x cubed minus y cubed. And that's how we're going to proceed to solve this next question. So we're given that this giant number has 2 primes. And what are they? So we should first be thinking about not to actually prime factorize this, but to use our previous factorizations. So our first one, x plus y squared, we really can't use that here because this isn't the sum of 2 squares probably. I mean, this isn't the sum of 2 things and then squared. This probably isn't a perfect square, so we shouldn't use that. For the next one, x squared minus y squared, we can try to use this. In fact, we can use this. It's just, it might be easier to do it in a different thing because it's going to be a lot simpler. So the one that we should be looking for isn't x plus y, it isn't sum of cubes, because once again this probably isn't the sum of 2 cubes. And yeah, so it's probably difference of cubes. Once again, we could have used difference of squares probably. If not, then oh well. But we can probably easily see that this giant number, solve in green, that giant number equals 8 billion. I think that's billion, I'm not sure. But yeah, it's got 9 zeros, minus 1. Okay, so yeah, difference of squares wouldn't work here, as you can see. So if we use this in blue and this in red, then we can see that this is 200 cubed minus 1 cubed. And then we can use our difference of cubes, which would be the quantity 200 minus 1, and then 4 minus, I'm gonna need more space for this actually, 40,000 minus, what notes plus 200 plus 1, and then we can, I'm not going to use this multicolored anymore. That's 199, which I think is a square. I hope. Wait. Okay, I made a mistake. So, actually, I'm just gonna resolve this. I'm gonna edit that part out. That's cool. If I don't, oh well, sucks to suck. That equals, I'll use that in blue, 2000 cubed minus 1 cubed, which then we can say that's 2000 minus 1 times 2000 squared plus 2000 plus 1. If I can, right, in that area. Cool, I can. Let's just say that's a plus 1. And we can simplify this. 1999 times, I'm just gonna write it down, 4002001, and because we know that this is a prime, we know that this must be a prime as well, because we're told that that ugly number has only 2 primes. So we solved our question. The 2 primes is 1,999 and 4,002,001. So with our next question, I didn't actually write it down yet. It's another Harvard, I think it's Harvard question. So we have x plus y over 1 plus z equals 1 minus z plus z squared over x squared minus xy plus y squared. X minus y over 3 minus z equals 9 plus 3z plus z squared over x squared plus xy plus y squared. And so what is x? Well, if we scroll back up to our, I just realized how ugly that is, our expansions, our special factorizations, then we can see that if we cross multiply, and I didn't memorize the question. Okay, so if we cross multiply, we get x cubed. Why did I put that equal right there? I'm just gonna x cubed plus y cubed equals z cubed plus 1 cubed. And you might be like, well, how'd you know that? Well, because we know that x plus y times x squared minus xy plus y squared is the exact form of, which one is it? X plus y. So this factorization right here. We're told that we're basically using that factorization, and we know that that equals x cubed plus y cubed, and we're using it 3 times. So x cubed plus y cubed equals z cubed plus 1 cubed. And then with our second equation, we can effectively do the same thing. But this time, instead of sum of cubes, it's difference of cubes. So we've got x cubed minus y cubed equals 3 cubed minus z cubed. And we can now sort of use some logic thing here. We're only given 2 equations and we have 3 variables. So the first thing that we should be thinking about is to not really solve for each of the variables, because that's impossible. If you have 3 variables, you must have 3 equations. So we should really be looking for how to use some clever things, I guess. And we can simply see, hopefully, that if we add the equations, this cancels and that cancels. So we've got 2x cubed equals 3 cubed plus 1 cubed, which equals 28. X cubed equals 14. X is, that's an arrow by the way, x is cube root of 14. And it's not plus or minus because you don't worry about odd powers with those. And checking our answer, wow, it really is that ugly. Yeah, so that's our answer. Cube root of 14. So, we can do one last question because we really only used the last 2, sum of cubes and difference of cubes, for these 2 HMMT questions. So let's just solve another one. Just add one. Pencil note, why not? Yay. I'm confused because I've never used that before. Let's say we're asked to, random number, 89, why not? So let's say we're asked to find 89 squared. Yeah, that's doable. So with our expand and factor, wow, okay. So we've got difference of squares, that's what we're going to use here. Oh, it's so annoying, I can't point here. We can use this one, difference of squares, and if I can switch it, that equals 90 minus 1 squared, which equals 90 squared minus 180 plus 1. 90 squared is that, and then you're subtracting 180 and you're adding 1. And that's really easy to do rather than simply doing 2-digit multiplication. So yeah, if we actually do the calculations, I hope I can do this properly. 7920. So answer is 7921. Next, let's say we're asked to find, rather than 89, what about 81 squared? Well, that equals 80 squared. That's dumb. 80 plus 1 squared. That's a parentheses, by the way. Sorry about the bad handwriting. This equals 6400 because that's 80 squared. I probably should not get ahead of myself. 80 squared plus 2 times 80 plus 1, because that's our sum of squares, which we are now actually using. Yay. This thing right here. So, if I can switch notes, this equals 64 plus 160 plus 1, which equals 6561. And that's our answer. So that's how we could use difference of squares and sum of squares to do bashy things like this, rather than actually multiplying it out. And let's go check if that's actually correct. 81 squared. I can't even spell squared. That's amazing. 6561. Did we get that right? If I can scroll down. Yeah, 6561. And then our second one is 89 squared. 89 squared is, if I can click enter properly, 7921, and we better have gotten that right. Yeah, 7921. So I guess that's how we're going to wrap up our video. We got it right. Yay. Cool.